All right, last class we had begun 3.3 and I want to finish that up today. And we had gotten to the point where we had created some examples of different models for multiplication, and we were at the point where we were going to talk about the different properties for multiplication. So the first property for multiplication that I want to talk about is the closure property. So this is just like when we did the closure property for addition. The idea is that if you have closure, it means you can add, in addition, you can add two numbers together and it stays within that set. So the closure for multiplication works the same way, and we're dealing against it with whole numbers. So if you have two whole numbers and you multiply them, the result is another whole number. And that should make sort of some sense, because remember, our whole multiplication definition was hinged upon the idea of being a repeated addition, kind of a concept anyway. So whole numbers, for every whole numbers a and b. We're going to try doing this without the access to the smartboard today. For every whole numbers a and b, a plus b is a whole number. All right, the commutative property is again very similar to when we were dealing with the commutative property in addition. So the idea being that when we have two numbers a plus b and they're whole numbers, then when we add them together, the order that we add didn't matter, and so it works the same thing for multiplication. I'm going to try typing, see if I can do better with that. So for our whole numbers a and b, ab is equal to BA. And if you prefer to see multiplication written there, we can say A times B equals B times A and actually see the multiplication signs, and that would be fine as well. And so then the next idea would be associative. So for the associative idea, whole numbers A, B, and C, this is the idea of parentheses, right? So if I have, let's do this in black to differentiate it. If I have A and then I have B, C, and I'm going to leave the x's out because they just start end up looking more like a variable, and that they're not supposed to be. They're supposed to be the multiplication x's. So if I had A times BC, that would be the same thing as having AB times C. And that is the associative property for multiplication. All right, we have an identity property, and this was our lecture, our last property when we were working in whole numbers with addition. And you can see, obviously, you've got a few others with multiplication, but the identity property is the idea that we have a number, and that number is 1, such that when we multiply by it, so 1 times A is equal to A times 1, and this is, of course, equal to A, and so it might actually look better to see that multiplication in here on this one, so let's see that. And that's the identity property. The zero property is the idea that if we have the number 0 times anything, it is equal to 0. And of course, again, just because this is commutative, again, it shouldn't matter, and in fact, it doesn't matter which side the 0 occurs on. When we multiply by 0, we get 0. We could have combined 3, 7, and 3, 8 together. They're awfully similar, and they're related to the idea of combining addition or subtraction with multiplication. So if you had a value that is being multiplied by two items that are being added, so something like this, A times B plus C, then this would actually be equal to AB plus AC. And it's almost an identical property when we do subtraction. In fact, I can copy paste this pretty well because I can just change it to be a subtraction in between, and the same idea holds. So this idea of being able to sort of draw a description of, over like this, these arrows, right, and multiply would give me what I would want when I'm trying to distribute multiplication over either addition or subtraction. So we're going to take a look at these, and we're going to identify which property it is that's being used and in which case. And we'll just identify it to the side. So on the first one, this is multiplication by 0, so we're seeing, of course, the 0 property. And let's do this in black as well. All right, so let's see here. All right, on the second one, we have 7 and we have a parenthesis. So again, don't get misled, just parentheses do not always mean that we have associative property. Because if you'll notice on part B, the 7 is outside of the parentheses on both sides. So the 7 does not move inside the parentheses like the associative property does. All that's actually happening is the 3 and the 4 are changing places. Well, when the numbers change places within multiplication, that is a commutative property. All right, so on the third one, we actually do see the 7 on the outside of 3 times 4, and then the 7 on the inside with the 3 and then times 4. And as we're taking a look at that one, the 7 sort of did move, or the parentheses sort of did move, and this is the associative property. All right, on D, we see that 3 times 4 times 1 is 3 times 4. So again, that 1 didn't actually change anything. That is the identity property. Okay, so on letters E, you see addition involved with the multiplication. So that sort of should be screaming at you that we've got a distributive property. And it's distributive property over addition because it is addition. And in fact, that's exactly what you see, right? You see the 3 and the 4 added together and the 5 on the outside. And then you see the 3 times the 5, and you see the 4 times the 5 combined with addition. So this is the distributive property over addition, of multiplication over addition. Enough space to write that, so let's pull this over like this. All right, last one. It sort of looks interesting because I don't exactly see any of the properties when I'm looking at it at just first glance. But they're there, of course. What you actually have here is you have 1 plus 2 and you have 3 plus 4. And they are multiplied together. So this is addition and multiplication. So this is going to be the distributive property multiplication over addition, just like on part E. But it looks a little bit different, right? Because this 3 and this 4, they sort of separate. What we're actually seeing happen, and let me use a pen to draw it, is we're seeing this 1 plus 2 distribute over this parentheses. So this 1 plus 2 ends up multiplying by 3, right? 1 plus 2 times 3. And then that same 1 plus 2 ends up being multiplied by 4. So this is 1 plus 2 times 4. So this again is the distributive property of multiplication over addition. Alright, so we talked about multiplication. There's another operation defined in this section, that is the idea of division. And we have this sort of same thing going on when we did addition and subtraction. We defined division in terms of multiplication, just as before we defined subtraction in terms of addition. So for any whole numbers A and B, and you have to have the condition that the B value is not 0, because we are not going to be able to divide by 0. So no division by 0. Then we have A divided by B equal to C if and only if C is the unique whole number such that B times C equals A. A is called the dividend. And B is called the divisor. That's what you're dividing by. And then C, the result of that, is called a quotient. And the different models for this aren't quite so obvious as being differently written, like with a word multiplication, but the image of what they actually look like is different. So what you get for a picture point of view for each of these will be different. All right, so we're going to take a look at the first example here for models of division, which is a set or a partition model. And your book actually puts this one and the next one, which is a set or partition model variation. They kind of include these all together, or you might even kind of say they omit the second one, but there is a distinctive difference that we will take a look at when we get more ingrained with not whole numbers that we're talking about, in particular when we do rational numbers in Math 2. We'll visit this topic again, and so I want to make sure that you're aware of the two ways of thinking about division. So take a look at this example. We have Abby. She has 24 rocks and she wants to give them to 6 of her friends. And the question is, how many rocks will each friend get? So you can take a look at this and you can actually sort of, kind of group these together. So she's got 6 friends, which means she needs to divide this evenly into 6 equal pieces. So we could sort of draw 6 equal pieces in here. And if we kind of split this up into 6 equal groups, then we can see, of course, that her friends get 4 rocks. Now, the second example that I said that your book sort of doesn't really draw attention to, but we need, it's going to use the same example. Okay, so here's our 24 rocks. I gotta move them without moving my type. Let's see here. Oh, that was not intended. All right, let's try that again. There we go, put those back up there. And I actually want to remove the divisions on this too, because it's not what we're going to do on this one. So the difference is the last one she had 6 friends that she was giving them to, so she divided them equally among 6 people. This one, though, notice, is the way she sort of is describing it. Instead on this one, she bags them together in groups of 6. So instead of giving them to 6 friends, she sort of makes 6 in a group. So she kind of groups them up. So there's 6 in this first group. And we have 6 in group 2. We have 6 in group 3. And we have 6 in group 4. And in fact, you notice then she's got 4 groups of rocks. So she has 4 friends that will each get a group of rocks. So what you'll see, the difference is between these, or you should see, is in one case she decides how many people get them and divides them evenly into that number of groups, and in this one she decides how many she wants to have in each group, and then she divides them up and decides how many friends get to have the rocks. Now the other 2 models, we're going to go back to the idea of giving them to 6 of her friends, and so this is the missing factor idea, and this one looks a lot like the missing factor idea for subtraction that we did before. So in this idea, what we want is we want 24 divided by something, and we don't really know necessarily what that something is. It's our missing factor, so we can put a question mark there, or we could put a box there as well, which might be more in keeping sort of with what some of the things are that I've seen my daughter bring home. So there's a sort of this missing box. And we can sort of decide then for ourselves what number needs to go here. And we can do this either directly, looking at this and remembering multiplication facts as a child, or this is a really good way to introduce what division does. In fact, we had this conversation, my daughter and I, the other day. What is division? What is its purpose? What kind of a problem does it help you solve? And you can do this in terms of multiplication, right? The definition of division is that this blank spot right here has to be able to be taken and multiplied by the 6, and it would equal 24. And so you can turn it into a multiplication problem, and then of course that blank spot, or that question mark, depending on how you have it, or X when you get into algebra, equals 4. So there are 4 rocks that each friend gets. Okay, so let's do the last model, and this last model is repeated subtraction. So repeated addition is an idea for multiplication. Repeated subtraction also works for division. So we have 24 rocks, and she wants to give them to 6 of her friends. So this, in just a moment. Let's actually alter this so that it looks like the same description that we had on the second one. I think that would make more sense in terms of what I'm about to do. So I'm going to take this and I'm going to change the direction so that it is groups of 6 business instead. Alright, this will work better. Alright, so 24 rocks, she groups them together in groups of 6. So this actually works a lot better for this description. The idea is that after she's created a group of 6, she no longer has 24 rocks she's working with. So we can subtract off 6 and she now has 18 rocks. And she's going to make another group of 6 and she's going to subtract it off, and so then she's going to have 12 rocks. And she creates another bag of 6 rocks, and when she does so, she has 6 rocks, which is exactly the last time she can subtract 6 evenly, of course, as well. We are working with whole numbers here, so we're talking about division that ends up being a whole number. And as you can take a look and see right here, we subtracted 6 4 times. Say it correctly. So let's see here, just a sec. So we subtracted 6 4 times, hence 4 friends received 6 rocks. So our answer then would be 4. Okay, so what I'd like for you to have done, if we had class today, of course, would be to create one of these for yourself. Create a word problem and solve it with the models. Now you'll notice that the word problem is not exactly the same, but it's very related for the different models. So I'm going to create another one here just so that you can see how this would work, and we're going to see how it goes. So let's take this model, and we're going to do here, I'll change the color to black as well, and we'll use Eli for an example. So Eli has, let's go with 10 friends. Okay, I have a better example actually than Eli. We're going to use myself as an example today. So Dr. Hands has, let's go with 8 students. I actually do have 8 students in Math 2 class. So 8 students in Math 2. She, as always, likes to form groups, right? You know that about me. So she wants to form, she wants to form 4 groups. How many will be in each group? So we could draw stick figures, we could draw whatever we'd like for our people. And that's what we'll do next. Let's see. Oh, that's a fun one. I haven't drawn hearts in this class, so we're going to draw our hearts as people. So we're going to do 8 people, and that's 4 of them, so let's do it again. Alright, so we have 8 people, and if I want to form 4 groups, then that means that I need to divide them in 4. Right, so I partitioned, this is actually a better description for what this method is. I partition them, I divide them up into 4 groups. So there are 2 in each group. So we're going to do the same kind of description that we just did for the second one, but the question will be asked a little bit differently. So, there's 2 ways that I can sort of form groups. One way is that I can have in my mind from the outset how many groups I want. So I have 24 students, I have 12 students, I want X number of groups. Maybe I have X number of problems, and so I want each group to have a different problem or have a different example they're going to do or something like this. The other idea is that I could actually want to decide how many people I want in each group. So I could actually set from the outgo, Dr. Hands has 8 students. She wants to form groups of, we'll say groups of 2. We're going to change the problem a little bit. So we're forming groups of 2. How many will be in each group? So the picture is looking very similar, but it won't look exactly the same because I'm actually doing it from a different perspective. So here's my 8 students, and instead of splitting them up into fourths, right, evenly into fourths, what I actually do is I go through one at a time and I make a group of 2. So here's one group of 2, here's a second group of 2, here's my third group of 2, and here's my fourth group of 2. And so I've got 4 groups. Now you have to understand that this would be done differently in a class, right? So if I wanted 2 in each group, like on this one, right, groups of 2, then I actually have to form them, and I say, all right, notice I did make just one correction while I had it paused. You didn't know I had it paused, but I actually changed this so that it read properly. How many groups will she have? Because that's actually the question I would be answering if I knew that I was making groups of 2. Okay, back to what I was saying. If you knew you were wanting to make groups of 2, which is typically how I make groups of 2 or 3 or whatever I decide, you actually have to pick the people who are going to be in each group. You see the partition model for doing groups done when you end up with somebody counting off. And we've all been in the experience where you say, count to 6, and you go 1, 2, 3, 4. All the 1s go here, all the 2s go here, all the 3s go here, and so forth. And so this one works really nicely even if you don't have an even number of people divided, because when you get to the end of the numbers, we just get however many people in however many groups, and they're divided as evenly as possible. All right, so let's take a look at taking this same example and doing our other 2 sort of descriptions. So the first one is having the, let's see here, let me get this typed in, give me a sec. Having the number of groups decided in advance. So this is a missing factors approach, right? We can take this and we can look at having 8 students, and we're dividing them, and we want to form 4 groups. So the question is, how many are in each group? So we can set up this missing factors. We can rewrite this as the block times 4 equals 8 if we choose. Either way you do it, whether you do it directly or whether you turn it into multiplication, you find out that this is the number 2. So there are 2 per group. The repeated subtraction approach, we actually would want to know how many people we have. And this happens to me quite frequently when I form groups. Undoubtedly, when I form new groups, somebody doesn't show up to class, and usually more than one somebody's. So I know that I want 2 in each group though, so I sort of make alterations as I go. And what I started with 8 people, right? And I take one group, and once I've decided that one group, I've only got 6 students left to choose from. And then I subtract a second time, 6 minus 2, and I have 4 students left. And then I subtract again a third group of 2 students. I have 2 students left, and those last 2 students then are automatically joined together in a group. And what you noticed is that over here I subtracted 4 times, so there were 4 groups. because I subtracted 4 times. 1, 2, 3, and 4. Those aren't my numbers, those are my subtractions. Alright, so the last idea that we're going to take a look at is those same properties that we had seen and whether or not they actually exist for division. So the first one is the closure property. So the question would be, if I divide any two whole numbers, do I automatically get a whole number? And hopefully you should very quickly decide that that can't work for very much the same reason subtraction didn't work with closure. Let's say I take the whole number 2 and I divide by the whole number 3. Obviously 2 divided by 3 is not a whole number, so there is no closure property for division. Community property has virtually the same problem. I could certainly do 4 divided by 2, and I can get a whole number in doing so, but 4 divided by 2, of course, is not the same thing as 2 divided by 4, which isn't even a whole number for us to be discussing. So could I come up with examples that worked? Yes, I can. If you take any number in itself, of course, it's going to division, and that will work. But in general, if the numbers are not the same, this is not going to be a property. The associative property has very similar problems. It's a little bit longer to write out to show you, but let me do an example. Let's say that we had 12 divided by 4. And then we divided that by 2. And then our question is, would that be the same thing as if we did 12 and divided 12 by the 4 divided by 2? So 12 divided by 4 is 3. So we have 3 divided by 2 on the left, which is already a problem because it's not a whole number. But on the right-hand side, you see that we've got 12. And 12 is divided by, 4 divided by 2, which is 2. So I actually end up with 3 halves, or 1 1/2 on the left. And I end up with 6 on the right. And of course, that's not okay. So these are not equal. So the associative property does not hold. All right, so let's take a look at the identity property. So the identity property, let me change colors so that we can see this a little bit more clearly. The identity property would have to have the property such that when I took a number, say 4 divided by 1, I get back the same number I started with. And that works great, right? 4 divided by 1 is in fact 4, but I run into problems if I try to do the division the other way around because this property, or this whole numbers, are not commutative. 4 divided by 1 does not equal 4. So we do not have an identity property. The zero property, again, so if I do 0 divided by 4, I get 0, and that's great. So it looks like the zero property is sort of standing a chance if I start this way. But if I then take 4 divided by 0, we run into problems because you can't divide by 0. And I haven't actually told you why, but this is undefined. Let me pause for a moment and explain why this would be the case. So let's consider the definition of division, which is 4 divided by 0 equals some number. And let's just put a box here. And let's turn it into multiplication. So if I had that box times 0, or 0 times the box, I have to be able to get back the number 4. And the problem is anything times the number 0 is not 4. I mean, I always get back 0. This side is always 0. And so it can never equal 4, which means it isn't possible even conceptually to divide by 0 because it doesn't have the inverse property sort of that multiplication would turn it into. So there's no 0 property. Now you'll notice I just put distributive property down here, and the reason I did is because the distributive property is going to either work or not work, either whether it's addition or subtraction. It doesn't make any difference. So let me sort of give you an idea with the distributive property. If you take the distributive property, so let's do 20 and 20 plus 10. And of course we want to be careful as we're doing an example that it's not sort of conjured up by accident that it would work. So we want to see if 20 plus 10 divided by 5 would be equal to 20 divided by 5. And then plus 10 divided by 5. All right, so 20 plus 10 is 30, and 30 divided by 5 is, of course, 6. Let's see here. On the right-hand side, we have 20 divided by 5, which is 4. We have 10 divided by 5, which is 2. And 4 plus 2 is also 6. So this works, and actually in general it will work with the subtraction. It will work with any numbers that you choose, and if we want to stick within the whole numbers, it will continue to work within the whole numbers. It actually works outside of the whole numbers as well. So the distributive property is the only property that we get for division that would work. All right, so we're going to do one example more, and this example is about Sue. Sue claims the following is true by the distributive law, where a and b are whole numbers. 3 times ab equals 3a, 3b. So you kind of imagine she's doing this to it, right? And the question is, how would you help her? So you should recognize when you're looking this at the get-go that we got an issue, and the issue is that Sue is thinking about a distributive property when we don't have any addition or multiplication. So the first thing we want to talk to Sue about is the fact that distribution relates, the distribution property relates multiplication, for that matter, or division. I'm not spelling well today. Let's try again, because we just saw the division property works, to addition, or we'll say it relates it with addition or subtraction. So this problem only has multiplication in it. So we could think of 3 times AB as a commutative property. So 3A times B, but not as a distributive property. And we can show her this very clearly with an example. So we can say something like, consider this example. So let's say we had 3 times 2 times 4. Well, 2 times 4 is 8, and 3 times 8 is 24. And so what she wants to say is that this is equal to 3 times 2 times 3 times 4. Well, 3 times 2 is 6, and 3 times 4 is 12, and 12 times 6 is 72. And clearly these two, 24 and 72 that is, are not equal. So her idea of distributing this, it will not work. Now we could verify as well that our idea of commutative property will work, which isn't a bad idea to do or talk about either. So let's do one more example. Let's say that we did what we were saying that we should be able to do, which is 3 times 2 and then times 4. So 3 times 2 is 6, and then 6 times 4 is 24. So the commutative property, as you can see, works just fine here, and that is the right property to use to think about this if you're trying to write it in a different form. So these two, right, they equal.